Today we will observe how the electromagnetic waves behave in a dielectric media. We have already studied about the Maxwell's equation. So Maxwell's equation governed the behavior of electromagnetic waves in any media. And we have also studied the second order differential equations called the wave equations. We will again study today. So we start with some basic terminology. We assume that our material is a linear material. That means the permeability and permittivity are constants. The medium is isotropic. That is, there is a symmetry in the medium in all the directions. It is perfectly homogeneous. There is translational symmetry in all directions. The medium is source free. That means the charge density is zero. The medium is non-conducting. That means the current density is zero. So these are the assumptions that we make for our dielectric medium. We start with the Maxwell's equations. These are the four Maxwell's equations that we have already studied, and substituting the value of the charge and the current densities to zero. The Maxwell's equation reduce these to these first four equations. We again take the curl of the fourth equation. You can see that the fourth equation is del cross E. We again take a curl of this equation and this becomes del cross E. We have added this del cross, that this del cross denotes the curl operator. By the vector identity I showed you yesterday, this double curl of a curl is equal to these two terms. And for our case, this term will be zero because del dot E is equal to zero is given by the Maxwell's first equation. You can see it here. This term will become zero. And already from the fourth equation on the right hand side, curl of this equation, we have this del cross. This is B dot. Dot representing the differentiation with respect to time. So when this term becomes zero, only this term remains. And on the right hand side, this term remains. The negative signs on both the sides cancel out. And the equation now becomes del square E is equal to curl of B dot. That means curl of del B by del T. Now from equation 3, we differentiate equation 3 with respect to time. The curl of B becomes the curl of B dot del B by del T. And on the right hand side, we have E dot, which becomes E double dot. It becomes E double differentiation. We equate the right hand side of equation 6 and the left hand side of equation 7 are the same. So from the equation 6 and 7, this left hand side of 6 is equal to the right hand side of equation 7. We take this term down the left hand side, the equation becomes what you can see in equation 8. We can write this equation again like this. And in the similar manner, taking the curl of equation 3 and adopting the similar procedure, we see that for the magnetic field, we have this kind of a second order differential equation. These are the wave equations that we talked of yesterday. And the velocity is given as 1 by under root mu epsilon, that you already know. And in the relativistic case, the velocity of light is equal to 1 by under root mu 0 epsilon 0. So from these equations, we see that E and B are the functions, and the del square minus mu epsilon del 2 by del T2 can be taken to be operator. We take E outside and let the other term remain inside. So we can see that this is an operator on the fields, E and B both. So this is a generalized equation that we can write for this. These two equations can be written in a common form like this. And this operator, this in the bracket, is called an Hertzian operator. So this is the wave equation or the equations of telegraphy. Now we aim to solve this equation. We start with an assumed solution. We take that electric field is of the type E0 is the amplitude of the electric field, and this is the oscillatory part. Omega t is the time dependent term, k dot r is the space dependent term, and phi is the phase. Since there is only one time dependent term and there is only one frequency, so we can say that this wave is a monochromatic wave. And if we substitute this equation into equation 8, this one, E, if we substitute the electric field here and perform these differential operators, that means we differentiate the electric field twice with respect to space, and the second term, the electric field is differentiated twice with respect to time. Just see here, this one. This is a differentiation with respect to space. This is with respect to time. So here we will get term of k, and here we will get term from omega. The time dependent term after differentiation will give us omega, and the space dependent term after differentiation will give us k. So that the equation 8 will now become this. So this equation, this kind of equation, a relation between omega and k, we get a relation between omega and k, and such relation is called the dispersion relation. Any wave equation giving us the relation between the frequency and the wave vector is called dispersion relation. And we can also write the electric field amplitude E0 in terms of components. This is a constant amplitude having constant components in x, y, and z directions. And corresponding to these constants, we will have the propagation vector in the three directions kx, ky, and kz. When we have already taken this, when we take the divergence of the electric field, just see, this is the electric field, we will take divergence, that means we will differentiate it with respect to r. So when we differentiate it with respect to r, we will get k outside, and cos, the differentiation of cos will be minus sign. So this minus sign will come also, and this derivation of the minus sign of the derivation of cos will become plus. So we have a plus sign here. We have this is positive, and the k comes from the differentiation of this term with respect to r. This is the k. And from another Maxwell's equation, this should be 0. And this can happen only when, from equation 19, this term k dot E0 is 0. What does this signify? The dot product of the propagation vector and the amplitude of the electric field is 0. That means they are the same direction. Now let us again look at this solution. This signifies that at a particular position R, the field strength E varies with the angular frequency. And the wavelength is related to propagation vector k through the relation 2 pi by k. Wavelength is equal to 2 pi upon k. This is the transverse wave. Likewise, we can have the value of the magnetic field also. We can have an assumed solution for the magnetic field corresponding to the electric field. Because electric and magnetic fields satisfy the Maxwell's equations simultaneously, so we will have a similar form. We adopt the similar mathematics and we get similar results. Combining both the two, we construct a wave, that's the transverse wave, where both the electric and magnetic vectors are present and both are perpendicular to each other and perpendicular to the direction of propagation. From these equations, we divide the equation, this equation by this equation, we get this relation. And this is nothing but the velocity that we had the relation before. In free space, the mu and epsilon has a value mu 0 and epsilon 0, which is equal to c. This is the velocity of light in free space. So you can see that the ratio of the amplitudes in free space is equal to the velocity of light. This is an important relation, that the ratio of the amplitudes is equal to the velocity of light. Now, this velocity of light can also, we can convert the magnetic B into H. B is equal to mu 0 H. We can convert this. This is the relation between B and H. We convert that magnetic field into intensity. And this ratio is called the impedance. And the impedance of the free space has a constant value of 376 ohm. And the refractive index, as you already know, is a ratio of the velocity of light in the free space upon velocity of light in the medium. Both substitute both the values in terms of mu and epsilon, we get the result in terms of the relative permittivity and permeability. So we see that the refractive index is proportional to the square root of the permeability. Now we know that every wave has some energy. We define that the energy of the electric field is given as a half epsilon E squared, and the energy density of the magnetic field is given as half mu H square. Note, this is the energy density and not the total energy. Now the electric flux that is the energy crossing per unit area per unit time, is given by E cross H. This is denoted by a vector, the product of E and H, the cross product of E and H is denoted by a vector called Poynting vector. S denotes the Poynting vector, and it is the energy flux, that is energy crossing per unit area per unit time. This is very important. S is energy flux, and that is energy crossing per unit area per unit time, not the total energy. So remember it. This. From the Poynting theorem and the Maxwell's equation, and having subsequent mathematics, we can arrive at these energy densities that we expressed earlier. We will not go into the mathematics in detail here. Just to remember that this is the energy density of the electric field, this is energy density of the magnetic field, and the Poynting vector denotes the energy flux crossing per, that is the energy crossing per unit area per unit time. The three relations are important. These three relations can be summarized and represented like this. And this expression is called Poynting theorem. This gives this Poynting vector, since it denotes the energy crossing per unit area per unit time. So this expression gives the law of conservation of energy. The Poynting theorem gives the law of conservation of energy at a particular area and at a particular time. At a particular area, I mean that the volume is bounded in a closed surface. So we end it here.